Hello, hello everyone. Welcome to CS549. Okay, I see now there are 38 people in the channel and more people are coming. Okay, so let's get started. All right. So I think first of all, you can see the updated slides that I have already uploaded to Canvas. And on the Canvas page, for this course, I will organize all the lectures, all the slides into modules. There will be 13 to 14 modules covering different topics in machine learning. And so in each module, you will find the slides in PDF formats and all the follow-up quiz assignments and the link to the recorded video will be also put into each module. Okay. And yeah, of course, for this semester, only for now, only the first 2 weeks will be online. Hopefully, we will get back to the classroom. Yeah, and also for the classroom, for the remaining weeks, I will also record. I already requested that recording form for the classroom. So there will be cameras in that classroom. And it's also my first time using that classroom. So it must be a fancy technique inside the room. All right, so yeah, let's look at our next slide. So for the a very brief outline for this course, we will cover basically 3 parts of content. The first part, as I put it, it's supervised learning parts, under which we will cover the logistic regression, which will be our basic model for binary classification tasks. And here afterwards is our the major parts of the supervised learning, which is neural network-based models. Okay, but this organization here, from supervised to unsupervised to advanced topics, is not in strict sequential order, in such an order. So what I plan to have, the order is that we do the basic models first. We do simple models like logistic regression models. And before logistic regression model, we can also have some slides talking about linear regression models, which are basically for simple tasks. Okay, so after that basic models, basic tasks have been gone through, then we will enter the neural network parts. Okay, but before we step into deeper content such as convolutional or recurrent neural networks, I plan to have the unsupervised learning parts also covered. Okay, so that is a bit different from previous semesters. I wish that we can have an overall idea of what kind of unsupervised learning techniques can be applied to different types of data, so that you can have a comparison with the so-called supervised learning tasks. Okay, and what comes next after the supervised and unsupervised majority part are covered, then we will mainly talk about 2 so-called advanced topics. First one is generative adversarial network, which is a very popular technique now, and a lot of the fancy effects we see online posts or in videos that, switch the person's face, switch that voice, and like algorithm generated arts and so on. These are or empowered by these generative adversarial networks. Okay, so that's something we will learn about. And the other advanced topic is transformers model. Okay, so it's a it's the basics for the state-of-the-art AI models to understand language, to understand human-composed text, or in natural dialogues as well. Okay, so that is a basic organization of the different topics in this course. Okay, and I will talk more about how the assignments, quiz questions, and exams and the final reports will be distributed, and the weight for each item at the end of the slides. Okay. Okay, so a little bit about myself. My name is Yang Xu, and I am currently an assistant professor of computer science in SDSU, and I'm a father of 2 kids. We go to hiking a lot. Yeah, so here's a picture of me and my families. And for research that I do, natural language processing is my main area, but I'm also very interested in general machine learning problems. Or in a different way, I'm interested in studying problems or solving problems that relate to data that can be used, that can be applied with machine learning methods. Okay, and also cognitive sciences in language comprehension, language production, computational linguistics. These are all kind of my broader interests here. Okay. If you are interested, you can visit our lab's websites to see some of our most recent projects and publications. All right. Okay, so as for the first class of this semester for this course, we will basically go through some histories of the concept of machine learning. Although it's a very young concept, a very new technique, but there's still some interesting insights that we can gain by looking back at how this technique evolves. Okay, and we will also go through or watch some videos about the most recent breakthroughs from mostly big tech companies, and also we will relate this back to what we're gonna will be learning during the course. Okay, so basically more about examples and introductory videos that we're gonna go through. Okay, and after that I will briefly talk about what kind of projects or what kind of practical problems that we can use machine learning to solve, and some of those are my ongoing work. And lastly, I would like to quickly go through the syllabus together, and if you have questions regarding assignments, regarding projects, exams, or other parts in the syllabus, you can raise your hand and let me know. I can answer that. Okay. All right. So a trend in the developments or evolving of machine learning actually can be traced or can be observable if we pay attention to several critical years. Okay, so the year of 2010, early 2010s, is a critical area, a critical stage in the area, because basically when we talk about machine learning before 2010s, the majority of the researchers in academia is basically using different techniques. Like the terms support vector machine or kernel methods are more popular, way more popular before 2010s. Yeah, but the area is reshaping or evolving insanely fast after 2010s, especially after the term or the technique of so-called deep learning started to show huge advantages over traditional methods. Okay, so after 2010s, it is the blooming of convolutional neural networks, recurrent neural networks, and afterwards reinforcement learning, generative adversarial networks, transformers, and all kinds of huge models started to enter the markets and started to shape into amazing techniques that basically change how we define the technique of machine learning. Okay. Yeah, several resources for your information if you are interested. Okay, so I did some simple research into the keyword search volume. Like we can see a very significant boost of how many times the keyword machine learning got searched over Google, right? It is kind of after the mid early 2010s, such an increase is incredible. Okay, and I marked the year here, 2012. We will look into the detail of that year because there's something interesting happening in that year. Here I said Neuro IPS 2012, so it is a name of a conference. And maybe at that year, that conference is not as, popular or well-known as current, compared to our current days. Yeah, but it is in that year, the famous data set called ImageNet gets published, and significant breakthroughs have been made on model performances on that data set. Okay, so we should mark this year, and it is after this year that different kinds of fancy convolutional neural networks got developed. Okay. Yeah. So this is from a chart, maybe from a meta research paper that compare the best performances on ImageNet based tasks. Okay, so first of all, ImageNet is a data sets that have millions of labeled images. Okay, and all these images contain basically everything in daily life, from objects, office objects, cars, planes, to animals, like dogs, cats, birds. So I think the full data set has 1,000 distinct labels. Okay, there are 1,000 distinct classes to be predicted by the model. Okay, so it can be imagined that it is not an easy task, especially for early days. You can see that from these charts, if we look at the red curve, okay, it's the best performance of the model measured by error rate. Okay, so 28% here at the year of 2010, right? It means that the best model in 2010 on ImageNet actually makes 28% mistakes. Okay, So that is not as good as human being judges. Okay, say if we have hired like 100, or we don't need that many judges. If we have two judges to classify the images in ImageNet, then we use the agreement between these two human judges to as a measurement of accuracy. Then we will almost get 100% accuracy. Okay, so what machines can do in that year, in early days, is not as good. Okay, far from satisfaction, far from ideal. Okay, but you can see that there's a dramatic increase from 2011 to 2012. Right, the best model in that year almost gets a 10% increase. Okay, so that is a huge improvement. Okay, it's improvements that's so big, it almost surpasses all the historical improvements we have made ever before. Okay, and the trend goes on after the years of 2012. Okay, so I guess nowadays the error rates will of course slow down, but it's already, I think for image prediction tasks, it's already surpassed. It already gets better, gets higher accuracy than human judges. Okay, because for some low resolution images in the ImageNet, it's sometimes also ambiguous for human judges to make predictions. Okay, yeah, and the field is developing so fast that different types of models that pushes the state of arts to a higher level each year, and that technique is applied to a broad range of different industries, not just stay in the lab. Okay, all the techniques that we can name nowadays in industry, like self-driving, like smart medicine, right? All those image-based tasks benefit from the scientific breakthroughs that have occurred after the year of 2012. All right. So another, actually within that year, the advantage made that enabled, so the technique, the background technique that enables this breakthrough is the application of graphical processing units, GPUs. And GPU is usually, as we commonly know, it's a device that handles graphic data fast than the CPU, much faster than CPU. So if you play PC games, video games, then a GPU is a necessity to support the rendering of your graphics to support high quality gaming. Yeah, but turns out that the deep neural network based models actually requires computations such as vector computation, vector dot production, matrix transformation of matrix, multiplication, all those computations, they are just very similar to the graphical computations that GPUs can handle very well. Okay, so that's the first time GPUs, or actually large number of GPUs, are used for training machine learning models. Okay, and the effect is, as we already seen, it's super good. Okay, so nowadays, when we want to train a computer vision based train a model for computer vision based tasks or for language based tasks, a GPU is almost always needed. Otherwise, we're gonna there's no way to train huge models or models of even medium sizes without a GPU. Okay. All right. So let's look into the question of why we need machine learning by basically going through some of those state-of-the-art, some of the most cutting-edge demonstrations from research labs or big tech companies, okay, so that we can have an intuitive idea of what machine learning-based techniques can actually enable us to do. So this is a AI day video from Tesla from last year. Okay, they have demonstrated some of the internal details of self-driving modules and how the different convolutional neural network models are applied in the street view recognition and different types of object recognition tasks. And also they have released several very powerful hardware devices to support machine learning training, to support the training of machine learning models. So let's look at it's a long video. Maybe I should jump into some episodes. It's not the demo that I want. Elon Musk talking.
Okay, hi everyone, welcome. My name is Andre, and I lead the vision team here at Tesla Autopilot, and I'm incredibly excited to be here to kick off this section, giving you a technical deep dive into the Autopilot stack and showing you all the under-the-hood components that go into making the car drive all by itself. So we're going to start off with the vision component here. Now, in the vision component, what we're trying to do is we're trying to design a neural network that processes the raw information, which in our case is the 8 cameras that are positioned around the vehicle. And they send us images, and we need to process that in real time into what we call the vector space. And this is a 3-dimensional representation of everything you need for driving.
Yeah, so he mentioned some critical concepts that what the machine learning model is able to do is to map the raw data captured from the 8 cameras, right, on the car, scanning through the surrounding environments. And the model is able to learn some representations that exists in the so-called vector space, okay? So he just mentioned the term vector space. So vector space is something that we will learn about in this course. It's basically a representation of all kinds of data, like image data or language data, into a high-dimensional vectors. Okay, when we talk about vectors, it's not like 3-dimensional, 4-dimensional, but like hundreds of dimensional vectors. And those vectors, they contain useful information that we can utilize to make predictions, to make judgments about situations. Okay. Let's see. Yeah, I like to show this
per pixel in order to actually do this projection. And so you can imagine just how high of a bar it is to predict that depth so accurately in these tiny, in every single pixel of the image. And also, if there's any occluded area where you'd like to make predictions, you will not be able to because it's not an image space concept in that case. So we very quickly the other problems with this, by the way, is also for object detection. If you are only making predictions per camera, then sometimes you will encounter cases like this where a single car actually spans 5 of the 8 cameras. And so if you are making individual predictions, then no single camera sees all of the car. And so obviously you're not going to be able to do a very good job of predicting that whole car. And it's going to be incredibly difficult to fuse these measurements. So we have this intuition that what we'd like to do instead is we'd like to take all of the images and
So here, there are two tasks basically introduced. The first one that we saw partially is to predict the road edges. Okay, so it's kind of an improved version of the edge detection in traditional computer vision techniques. Yeah, as a traditional computer vision techniques, I mean, we can, by given you a image, static image, we can detect all the existing edges in that image by simply applying some arithmetic operations on the pixel values in that image. Okay, so we can do that. We can already accomplish that in 1980s without even applying the machine learning techniques. Okay, but the tricky parts in real time edge prediction here is that we want higher accuracy and higher robustness in the of the system. So actually, there's actually a vector space representation for the road edges generated.
Simultaneously feed them into a
And the second task is to recognize surrounding cars, right? And because the cars have different sizes and the camera on each car, on the self-driving car only can scan part of the space. So it's necessary to combine the predictions from different cameras to fuse into a single prediction about whether there's a car at some direction and how big that car is, kind of like these tasks. Okay. And let me skip to the scenario reconstruction. Yeah, let's see if this is interesting.
That happens to the autopilot in simulation so that we can hold autopilot to the same bar from then on. So here on the left side, you're seeing a real clip that was collected from a car. It then goes through our auto labeling pipeline to produce a 3D reconstruction of the scene along. In order to do.
So yeah, so that's the software parts, and maybe we can look into the hardware. Yeah, newly released hardware that Tesla has published. Huh?
And in fact, last week, we got our first functional training tile. And on a limited cooling benchtop setup, we got some networks running. And I was told Andre doesn't believe that we could run networks till we could run one of his creations. Andre, this is MinGPT-2 running on Dojo. Do you believe it? Generates code on the fly.
Yeah. Huh.
And next up, Elon will update us on what's beyond our vehicle feed.
Okay, so yeah, hopefully this gives you some ideas of what machine learning based models can do, kind of accomplish nowadays, and that's just a one small product show from one company. Okay, and big techs like Google, Facebook, Amazon, Microsoft, they all have their own very mature and very big ecosystems, software ecosystems built around the machine learning tasks. Okay, but different companies have different focuses, like the Google Brain or the DeepMind, which is a company under Google. Okay, so it's basically a company that's focused on AI-based strategies, like AI-based gaming strategies, gaming algorithms. And for Facebook, it acquires the famous machine learning framework called PyTorch. It's actually developed by the Facebook team at the beginning. So that is the framework that we will use for this course. Okay. All right. Let's go. Yeah. So here I showed another example from a different company. So it's also a famous company called OpenAI, and it's I think 2 years ago maybe it's get very popular because of it releases some models that have been trained with reinforcement learning strategies to train AI models that beat human video game players. Okay, so that's a very popular news at that time. And actually, this company is doing more than gaming models. And the post that I post here, DALL-E, it's actually an interesting application of how the different types of tasks can actually be merged into one interesting application. Okay, so what this model can achieve is that we give it a text prompt. You see the prompt here, right? We can type into a text prompt, say, hey, an illustration of baby daikon radish in the tutu walking the dog. So that's pure text inputs. But the model, the DALL-E model, is able to generate a series of images that satisfies or that understands the meanings of the textual inputs. Okay, so you can see in all of these 5 outputs, we see a dog, right? A baby daikon radish, right? And the baby daikon radish is wearing a tutu, right? And he's walking the dog. So that's an amazing output, actually, amazing performance. But we don't know what kind of data this DALL-E model has been trained against, right? So it must be a collection of different cartoon images, and also training against images is not sufficient because the model needs to first understand the textual, the meanings of these textual inputs, right? So it must be a language model also integrated into the final model. Okay, the model needs to understand, hey, what a dog is, right? Given the dog, the 3 letters, it needs to generate some outputs that looks like the real shape of a dog, right? And all of these beautiful outputs can be is actually generated by the model automatically. And the second example is here. We want the model to generate something like armchair in the shape of an avocado, and the output is also interesting. Okay, so these outputs can actually enable the computer systems some functions that we even did not imagine about. Like these kind of applications actually is a game changer for designers and for different styles of artistic creation, right? So it's because when human beings brainstorm, like when we sit together to brainstorm, hey, what kind of a armchair should look like if we want the shape of an avocado to be integrated, Okay, so that takes human intelligence, takes very experienced art designers, right? But if we can get some assistance from a machine learning model like the Wally, like the DALL-E model have demonstrated here, it'll be a super cool application that even people without the training, without artistic training, without experiences in art creation can get access to such a capability of this creative thinking. Okay. All right, so that's the second example from OpenAI. And more OpenAI examples can be found on their websites. Okay, so this one is a example for generating musics. Okay, that's something you can check it out. It's kind of similar to generating the pictures or languages in the previous slide here, right? All these models are trained with sequence to sequence functions emphasized. Okay, another OpenAI example. Yeah, they also do robotics researches. Okay, so they trained these electrical or mechanical arm to play the Rubik's cubes. Okay, and it's other than the computer vision and the sequential modeling parts in this system, they also something related to reinforcement learning also integrated. Yeah. Okay, we're gonna skip this real quick. I would encourage you to watch some of those most state-of-the-art techniques from openai.com. Okay. Yeah, Waymo, I'm gonna skip this. That's another video from, I guess it's from Waymo, but it's years ago. Yeah. So basically we can see that when a car is going, self-driving car is going, is driving on the road, there's actually some internal representations learned, right? So you see that those cubes in purple. So these are the representations for the incoming cars or the cars beside the self-driving car. Okay, and the illustrated green roads and those green traffic signs or representations within computer memory. Okay. Yeah, but I don't think this is the most recent advantage, the most recent designs. The demo from Tesla is more recent, but this is one of the most classical prototypes years ago. All right, yeah, and we mentioned a bit about DeepMind from Google, right? Still remember that years ago, it should be 2018, when the AlphaGo or AlphaGo Zero, the year after, was developed to beat the human experts in the very well-known difficult games called Go. Okay, this is a historical breakthrough. Yeah, because it's not a rule-based AI. When we talk about rule-based AI, we already cannot beat computers back into 1980s or 90s when the IBM's computer can beat the world champion, right? That was a famous example years ago. But the AI at that time was rule-based or search-based. All the how the chess moves is actually coded into not decision tree, but into policy trees. Okay, but because the game Go is way more complex than the chess, so before the deep neural networks or deep policy neural networks comes into application for this for this game, people actually can hardly believe that the AIs can beat human players. But it was amazing breakthrough. By simply applying several neural networks, one trained for the value, one trained for the policy, and we will let the AI model or the machine learning based model to play against itself. We will receive a state, we'll go to a stage that it can outperform even the world level, top level human champions for such a game. That is one of the most remarkable achievements of AI or machine learning based techniques. Okay, we actually have several more examples. Deep fake videos, this one is something we should know about. It not just creates hilarious examples, but also it brings very serious concerns about how the machine learning techniques should be used properly, or should conform to the our moral concepts. Okay, because such a technique can so easily cheat, can so easily conceive people. Let's see how the face change effects. Okay, oh, this is a static image. Oh well, so I will not play the video here. So this is something that we will talk more about when we introduce the advanced topics, the GANs. GANs is one of the techniques that can be used to switch faces or to generate some human faces that have never appeared or you have never seen before. So yeah, let's skip these two videos for now. All right, so that's already a lot of examples. So if we want to summarize what machine learning is, actually it's not an easy thing, right? But we have something in mind that it has to deal with a lot of data, right? Otherwise, there's nothing to be learned, right? The models needs to learn from data. Well, when we have data, and then we will have the learner, which is the model, right? So that is the two most important concepts in defining machine learning. Okay, so if we use the quote from a philosopher, Arthur Samuel, in 1950s, actually, I think it summarizes the machine learning capability actually pretty well, pretty precisely. Okay, so it's actually the study that tries to enable the computers the ability to learn, and that ability is not hard programmed, or it's not explicitly programmed. In another way, this ability to learn is actually dynamically adapted. Okay, it's not preset, it's dynamically obtained or acquired from the environment surrounding the algorithm. Okay, in 1998, I think the paradigm proposed by Tom Mitchell is a good framework to basically cover all types of machine learning tasks nowadays. So he used the term experience, capital letter E. Okay, so the computer program can learn from some experiences. Okay, and I would say this experience is actually another name for data. Okay, but it's not if we use experience, it's not like materialized into something we can see or we can directly observe. But it's kind of the similar concept. And we need also, other than experience, other than the data, we should also define some tasks. Okay, so without a clear definition of task, the model will be confused. The computer program will be confused. It doesn't know the direction of training, doesn't know the direction of learning. Okay, so the task is also important. Okay, so lastly, the third one is called the performance measure, P. Okay, so P, performance measure, is also important because it's kind of the critical issue that we human beings, the one who train the model, needs to use to guide the training or to know when exactly to end the training. Right? We need to know the models at certain points. It's getting better or getting worse. Right? Without that standard, we will never know whether we should end the model and the training or not. Okay, yeah, more examples. So let's use the experience task and performance measure as a way to, categorize or to rename some of those tasks. Like in the case of a face recognition, we want to either recognize the emotions of a face or simply to recognize the identity of a face, whether the face belongs to a person or not. Then the experience in this case is the face images from one person, right? Then the task can be that we want to, given the unseen image, we want to make prediction or to recognize if that comes from the same person. And lastly, the performance. Well, in this case, it's right or wrong, right? Either the same person or not the same person. Then we can use simply the accuracy to make the as the performance measurement. All right. So here in this slide, I want to show a chart that I think found very useful to understand what the so-called machine learning is, or to summarize what the process is doing. Okay, so by running a machine learning algorithm, we are actually building a model of the world. Okay, and this model consists of a bunch of parameters. Okay, and we use Greek letters theta1, theta2, theta3 as the representation for the models. Okay, and the model need to learn from the data. Okay, say we have collected on the left here, represented by these blue boxes, and we call them data packets. Okay, and we should let the model to learn from those data. Okay, and because it's a lot of data, right? So maybe each time the model will only pick a small batch or small packets from the total data sets, right? So that's usually how the model behaves, right? So after the first data is picked, the model will pick the next and the next, right? Until the training stage or the learning stage is done. Okay. So after the model has gone through all those data in the real world, it is fixed, right? We should, at some point, we should fix those model parameters and we don't change them anymore. So what's left is to examine how the learned model perform on some new data sets. Okay, right? So in the case of predicting whether the email is spam or not, we should grab some new collection of emails. And we will ask the model that we have just trained to tell whether this new data is a spam or not, or whatever other tasks we have. Okay, so that's a basic paradigm for understanding or to have a overall picture of what machine learning model can achieve. Okay, so hopefully these slides can help you to build some mental concepts, mental images of what machine learning process should look like, right? So you should have the idea of that. Okay, we need to have some parameters, data, new data, and stuff, right? Okay, right. So more examples. We just mentioned the spam email detection, right? And same examples can be applied to different tasks, like sentiment classification. Given a task, given a post, tweets, we can predict whether it's positive or negative, right? But with different scales. And language model, right? So here I will introduce some of the my research work. Okay, the first one is the language used in dialogue. Okay, so language modeling, it's kind of different from the previous model, like to predict the spam mail or not. The targets of a language model is the large body of text inputs. Okay, and the task is to predict how likely the upcoming new word to be. Okay, what kind of word or what specific words the next word would be. Okay, so we kind of want to measure the probabilities of the word this, right, after the who gave, and the word book after the word gave this, and so on. Okay, so these the log in this particular example here, we compute the logarithm of the probabilities of such words, and the summarization, the summation of these logarithms will be the so-called entropies of the model. Okay, and the entropies of our each sentences will be useful indicator of how well the dialogue is going and how well the collaboration between speakers can be. So that is part of my research work. Okay, and we use the second case is from the first research here. We can use the spectrum representations of the two series to make predictions about how the collaborative performance between two speakers can be. Okay, and I also use language style to connect with social powers. Okay, but that is not totally related to machine learning, but the entropy measures, as I mentioned above here, yeah, can also be an indicator of social power, but that is something left to be examined. Okay, so we usually would believe that when the two speakers in different social power statuses, like someone is in charge, someone is more listening, then the language used by these two different social classes, persons, may also be different. So that's something I found interesting in my research. Okay. We can use a logistic regression model in this case to predict the social classes given an input language, inputs sequence, right? All right, so that's the first three cases, and the fourth case of our current ongoing lab research projects is in the new field of medical imaging. So given a video or a static image of blood cells obtained from medical cameras, we can actually observe or calculate calculate the flow of blood cells, or we can measure the size of the chunks in the blood cells, okay, without doing invasive operations on the patients. Okay, so that is a critical improvements over that machine learning techniques can bring us. Okay, without such a technique, we have to do a lot of experiments, a lot of slow and sometimes risky operations. But if we can make these applications more mature and having the algorithms more stable and accurate, then that will be a really interesting, really promising applications for future medical techniques. You see, after we have stabilized the video and we can more easily track the velocities for each moving blood cells. Okay, and the velocities of blood cells and the chunks of the blood cells can actually be useful medical indicators. Okay, here it's a more stable example here. We can compute and plot the velocities for all the moving blood cells. Okay. And the last research question that I would like to introduce is the study of real-time human languages, but in a multimodality style. Like when we talk in front of the camera or in front of other persons face-to-face, it's highly likely that we will move our bodies or move our hand in order to convey some ideas. And the hand positions, the different gestures, they actually carry different meanings, okay? And the purpose of this study is to look at how we interpret the meanings of the gestures together with the language that we use at the same time, right? For example,
there's one thing that I recommend.
The video is broke here, right? You can see that when the person talks, his hands moves, and we want to extract the body joints, the key body joints, and then more importantly, we want to represent those body movements into a vector space. So, right, for each frame, we can extract some gesture position, and we want to carry out some maybe some clustering algorithms to see whether different types of gestures, they have kind of similar meanings, right? And if this is the case, then we can interpret the meanings of gestures. Okay. So that is another part. And lastly, for financial forecasting. So that's a one of the projects that I wish to introduce for the final projects in this course, because there's interesting sequential information involved, sequential data involved, and we can easily apply some of the recurrent neural network models on this task, and it'll be an interesting output to see how accurate we can do, like how accurately we can predict not just the market price, but also the big decisions like whether a company is going to be incorporated, going to be acquired by another one. Such a information will be really interesting for financial science researchers. Okay, so we can summarize what kind of machine learning models can do, and more importantly, I think is this simple mental model that we should all have. I think it'll be a very helpful mental model for the take-home message for this first course, right? We want to train something called a model that's here, represented by a bunch of parameters from observing all those data. And after the models are trained, we want to use these trained parameters to make predictions about new data, okay? And let's go to the syllabus, okay? So first of all, we'd like to talk about grading policy. We will have programming assignments that takes 50%, and there will be 10 program assignments, one covering each topic, and the assignments will be released in Jupyter notebooks. It'll be great if you have previous experiences using Jupyter notebook, but it's also okay if you're not. We will have one lecture covering that topic. We will have a final exam that takes 20%. Questions will be basically multi-choice questions, and it'll be an open book. So it'll be a test of machine learning knowledges covered in the lecture slides. There will be 10 assignments. 10 assignments in programming Jupyter notebooks. And for the final group project, it takes 25%, and I will release the available topics for you to choose from, and you need to group up with 2 to 3 persons as one team, okay? And you need to choose one topic and implement the models required for that task, okay? But you have freedom to choose some of the model details. The exams will be in person. I see a question from the Zoom chat. Okay. And also there will be some short quiz questions after each class. I will release those quiz questions on Canvas also. Okay. Okay, yeah. So far I have for the group projects, I have something in my mind, and I am finishing up the guidelines for each project. So basically, you can choose from these projects. Like either you can do a blood cell detection using a object detection model, or you can do financial data prediction. It's a sequential data, and it's actually a collaboration with a faculty from University of San Diego. And for the textual analysis using transformers, this is also an interesting application of machine learning techniques on different kinds of text data. So in our case, I will include some data for the conferences, from company conferences. That's maybe a CEO talk to different stakeholders of a company, and we can use that to analyze how the conversations can actually affect the company's performance and so on. Okay, so that's it for the slides. And let me share the screens, share the syllabus. Maybe there's something we should talk about in the syllabus. Okay, so there will be 10 assignments. covering each topics that I listed here. Okay, so the last assignment will be due around the 14th week. Okay, and my plan for the last 2 weeks is for talking to all the teams for projects for the group projects, and we will do some review for the final exams. Okay, so for the last 2 weeks, we will not have assignments due, and I do hope that we can have some discussions in the classroom about each group project team. And the team up phase, I think we should have that done by the end of February, by February 24th. So I hope before that you should talk to you should find the teammates, find a team from the classroom, and each team can consist of 2 to 3 students. And for group project selection, that can be done at the later time. The date that I put here is April 5th, because at that time we already have gone through all the basic stuff in the course, and you will still have time to choose the models, to choose the architecture, and to choose the to implement code that's actually can that first successfully run and also successfully train the model. Okay, and for the final exam, we will use the dates listed by the SDSU website. So it's May 10th. And I will give some additional time for you to compose the group projects reports. Okay, so it'll be due on May 15th, which is a Sunday. Okay. Yeah, so please do read the syllabus and let me know if you have questions. The best way to contact me is to go through to use this email. Okay. And I think we already have 63 students in the classroom, and say all the teams have 3 students, then that'll be 20 teams. So that's a lot of numbers. So I'm not sure whether we need to do a presentation in class or not, but we will see. We will see. So I want to talk to each team, at least 2 times. We can do that during the last 2 weeks and between the middle of the semester, so that we can select the topics that better suits everyone's interest and everyone's needs. I see a message. Will you be providing data set? Yes, I will be providing data sets. So the topics for each projects will be predetermined. Data sets will be provided. Is there any TA? Yes, there is a TA. I will send emails to you, and the TA will answer your questions. I will make an announcement in the Canvas about the TA's information. So the TA will help you making makes the team up phase easier, and also he will grade all the assignments. The question regarding required textbook, no, we don't have a required textbooks. All the materials listed in the syllabus are optional. I don't think there is a book that you should necessarily read, because you see, although I listed the Goodfellow's book here, the Deep Learning book, which is a famous book, but I think it's a lot of math. It's of course it'll be helpful. It'll be helpful if you go through the details. Yeah, but I don't think it's required. It's not required. There are no there's no assignments due this week. Okay, I will release the first assignments next week. Okay, usually all assignments are due in a week's time. Another question regarding wait lists. Yeah, unfortunately, I don't think I will add more students. Add more students. It's already a very full classroom. Someone opened a Discord server. That's nice. What is the likelihood that waitlist can get into the class? No, I'm sorry about that, but it's already 60 students in the classroom, and we're doing group projects. I don't think I will add more students to the classroom. Okay. Are there any questions about the course? Okay, so if not, I'm going to end the class now, and I will upload the video and put a link to the Canvas page. Okay. So for all the courses in the first 2 weeks, I will do that, and for all the future courses, I will also send out a link for the recorded classroom.
Is the final project also a programming assignment?
For the final project, I will not provide code templates. That's different from the code assignments. For all the 10 assignments for each during the semester, I will provide a templates Jupyter notebook that you can fill in the code. Okay, I will have a code frameworks layout, and then you can fill in the missing code and then execute the cells in the Jupyter notebook to see if it's a correct answer or not. Okay, but for the final project, I will not provide such a code framework.
Okay, thanks.
Yeah, that's a good question. Will the final exam will be in person. Will be using libraries like sklearn for assignments. I don't use sklearns for assignments, for developing algorithms from scratch, it can be difficult if it's a huge model. Like if you want to develop a complete convolutional neural network that supports forward pass, backward pass, that's not necessary. I don't have assignment like that. But for simpler models, for logistic regressions, linear regressions, we need to understand the mathematical details. Then yes, we will have more from the scratch implementations for such models. Yeah. And I don't use sklearn, but we will use PyTorch for more complex models. Okay, and for unsupervised learning part like clustering, we will have an assignment that implements part of the k-means algorithm. But well, maybe I should correct myself. For the k-means parts, we can compare our k-means with a sklearn. Yeah, I do remember that we have some little sklearn coding there. Is there any software I should download before the next lecture? Yeah, so you don't need to do that before the class. We will go through that steps during the class. Okay, and because basically all the videos will be recorded, so you can watch it later if you need more guidance in installing softwares. Okay. There are other questions? All right. Okay, so I'm gonna end the recording now.